Well, thank you all for coming this morning. My name is Vince Liberia. I work for the IKONICS Corporation in Duluth, Minnesota. And today I'm here to talk to you about traditional and alternative machining methods for perforating composite materials. And in order to do that, we're going to talk about a variety of things. We'll start out talk a little bit about the growth in aerospace composites, challenges perforating composites, traditional perforating methods and the issues associated with that. Then we're going to get into a unique and alternative method for doing that, and that's something that we're going to spend a little bit more time on than the other items. I'll give you an idea of the process overview and the benefits that are realized from this alternative method. And then I want to talk a little bit about some external laboratory testing that we've done, not only through independent labs, but also NASA has done some studies that you'll find interesting results that came out of that. Then last and not least, we're going to give you some real examples and applications about how this new approach is being used in the industry. First, we're talking about composite growth. And there's a significant increase in composite growth, and I think everybody understands that, particularly in the aerospace industry. And there's a lot of pull factors, drivers that are causing that to occur. One clearly is weight reduction of the aircraft, which translates into better fuel efficiencies. And last but not least, structural strength is very important. So you can't have one without the other when you switch over to composites. Now, the challenges associated when you perforate composites are a lot different than with metals. For example, you're dealing with non-homogeneous materials. These materials are made up of fibers, epoxy materials, and they're also multi-layered. Different kinds of fibers, which create a lot of the thermal mismatch when you try to machine these materials. So that's certainly an issue that we have to be concerned about. They often require secondary processes. What I mean by that is you have to remove a lot of burrs that are generated when you machine composites and loose fibers, which you don't want floating around in your equipment once you've done the perforation. Delamination between composite layers is an extremely challenging issue because when that occurs, you don't repair that composite. You essentially throw it away. So that's really a major issue. And as they get more dense with the holes that are put in during perforation, in other words, holes are closer together, that tendency for delamination becomes even more critical with the traditional methods for machining. And last but not least, heat and invisible stress damage. This is something you don't normally see until after the composite has been done, perforated, and then it's been tested. So these are challenges, if you will, associated with perforating composites with traditional methods. Now, ironically, having said that, the other issue, see, there's a problem right there. I forgot this last issue, is cutting tools wear out more rapidly. That's an important point because the drills, for example, in CNC machining will wear quickly and cause a lot of the problems that I've highlighted above. Now, ironically, the typical specifications that are often put onto the perforation product is that the holes and the feature sizes have to be uniform. Okay? They can't have any burrs or loose fibers, and we just talked about that as a challenge before. No delamination of layers, again, a challenge with traditional methods. And no distortion or stresses built up in the composite. No lost or missing holes or features, which often does occur with traditional methods. In other words, you don't have all the holes or features that you want in the composite. Okay? So that is a specification that is required by the aerospace industry for perforating composites. Here's some typical applications. You can see and read those as easily as I can, but the most critical one here is associated with the engine itself, particularly with engine liners. You cannot have these defects in perforated composites when you're putting them in the engine itself. There's other applications, of course, that are just as critical, but clearly that is the most critical. And typically what you see in the industry for machining composites or perforating them is CNC drilling, which is the most popular one. That's the mechanical drilling into the composite. Water jet is also a popular one. And a much less popular one is laser drilling. And we're going to talk about these three and the issues associated with them as we go forward. Let's first talk about CNC drilling, the most popular one out there. And as you can see, what happens is initially, when you start to drill, you'll see things like fibers and burrs associated with the drilling process. You'll see here there's tearing of the wall inside of the hole. A lot of things, you don't see these necessarily unless you're looking under a microscope. And as the drill wears, you start to see this uniformity problem where the actual hole sizes will vary and change over time. Now, this is just showing a close-up of that sidewall, and you can see the burrs and the loose fibers that exist in here. And again, you don't see that until you're looking under a microscope, okay? Second method is water jet drilling. This one is also popular, but not as popular as mechanical drilling. And the major issue here is that it's wet, all right? Composite materials don't like a lot of water, okay? And so what happens when you're trying to drill a composite with water jet, you actually get water down inside the holes, which causes the composite to delaminate. And that, of course, becomes a major issue, and it is not reparable when that occurs. Also, you have loose fibers in here. You have size uniformity, which is also an issue with water jet drilling. So these are issues that maybe can be overcome in time, but right now are issues. Not so much with metals, but with composites. And the last one, which is really the least popular and not often done, is laser drilling. And they're trying to get this more into the industry, but there's a major issue here. We talked about that thermal mismatch before between fibers, epoxy. So you can't get the right energy balance into the laser in order to get a good uniform image without causing burnishing, heat, stress, delamination, and again, very hard to repair any of these if they occur. So that's why this one is not as popular as the other two methods are. Now we're going to focus on is that alternative method I indicated earlier, which hopefully, we believe, gets around most of these issues that we've just talked about. It's called precision abrasive machining, PAM for short. And basically what that entails is that it's a unique, non-traditional dry perforation method, and the key word here is dry, okay? It can produce a variety of precise features. Another key word here is variety. It doesn't have to be a round hole. It can be any shape, any size, because of the way it's produced, and we'll show you that in a minute. It's all these are done in what we call advanced or brittle materials. And some of those that we talk about, I'll show you in a second. It does all this while not imparting any heat, stress, or damage to the material, okay? So that's a key point, because if you go back to the original specifications, those were critical that we would meet those specifications. The kinds of brittle materials we're talking about are anything from composites to glass, quartz, silicon, sapphire, ceramics, silicon carbide, very difficult products to machine. This method allows you to do this a whole lot better than you could do with conventional techniques. But today what we're going to focus on is composites. The machining process that we're talking about is compatible with all kinds of composite materials, including fiberglass, carbon fiber, even Kevlar, and some of the ceramic matrix composites. And again, as I said before, even though most of them are done with typical round holes, this process will allow you to perforate any feature size, any size, into almost any composite material, okay? How is that done? Well, actually, it's taking existing technologies to create the unexpected. And you'll see why I say it's unexpected here in a moment. The first technology that we talk about is using the precision of a photoresist technology. Now, those of you who are familiar with the electronics industry will understand what that means. I mean, these people are making wafers and semiconductor materials processes down into the micron levels in terms of their precision, okay? So you take that ability to do that precision and you combine it with something that people look at you kind of cross-eyed when you say that, sandblasting. One of the more crude process that you would think, never could I use this process in combination with a photoresist. Well, in fact, you can. And I'll tell you how we do that. The key here is we start out with a photoresist that's shown here in red. Now it is a unique photoresist, okay? It has specific properties that after you have gone through the photo imaging process, which is created on your computer, that means you can create any image, not just round holes, but any image on there. You can see here there's some rectangular parts, larger holes and smaller holes. Create that onto the photoresist and then apply that to the composite material, just shown here in black, all right? So now you've got the precision of all those features in that photoresist. And then what you do is you combine that with today's advanced technology for robotics, where you can have 5, 6-axis machines that actually have sandblasting heads on them instead of drilling heads on the end, all right? So that allows you to now blast through that mask, and you're thinking, my goodness, what's going to happen to that mask when you blast it? And the answer is not a whole lot, okay? And what we're going to do is we're going to show you just in a very simple schematic format here. This is a flat panel that has been laminated with this red resist that has the holes in it already. And then this is just a typical 2-nozzle sandblaster. And what you'll see here, just to work, there we go. We don't blast one hole at a time like you would typically drill one hole at a time or water jet one hole at a time. We do a scanning approach. So we're not imparting a lot of stress to this substrate while this process is going on. And that's a key point here. So what we're doing is we're gradually putting those holes through the substrate because the abrasive is going through the holes in the mask and starting to abrade away at the substrate, okay? Now take that and project it into something that we can all relate to. Here's a liner for a jet engine that has these resist applied to it that's already been imaged with the holes, okay? And here is the robotic system with sandblasting nozzles on the end. Now what's kind of neat is, you look at that and you say, well, that's all very nice, but let me see that in motion. So let's go ahead and let's put that in motion. There we go. And now you can actually see what's happening. The nozzles are scanning across that photoresist, and that will go entirely around that liner. Several hours later, all those holes will have been blasted very gradually, and I'll show you the process of how that works. But that's essentially what's going on here. And the mask, this photoresist that we have on here in the red, is resisting the abrasive, and it's only going through where the film was imaged, okay? When you're done, you remove the mask, and remember the mask has protected the entire substrate during that whole process. And so what you can see here is this is just a section of that liner that's been removed, and you can see how uniform and clean all those holes are. No secondary processes are needed. There's no burr. No stresses have been put into the material, and it's ready for use right after blasting. Okay. Now this chart's a little busy, but let me take you through it because it really explains how the process works and why we end up with so few stresses or damage to the material. What you're looking at here, this is a top view where the mask has been applied to the substrate, and the red is the mask, and it's been imaged so that you see the round opening, which is the same size for each of the holes in this particular case. Taking that and looking at a side view, the way the process works is as you start to blast, you start to erode away at the composite material, and the more passes that you do back and forth, the more that material gets eroded away and eventually comes all the way through the bottom. Now you say, well, gee, it's not a straight hole. No, that's right. You always end up with a taper. You can get it down to about 6 degrees, minimum taper here. It starts out at about 35 degrees. And the reason for that is because as you blast from the top to the bottom, you actually lose energy as you're blasting. So you're going to end up with less energy to remove the material on that sidewall. You say, well, gee, that's going to be a problem. Well, the fact is that in some applications, that's actually an advantage, because acoustically, you can possibly tune this to create a more acoustical effect and sound deadening when that taper is the right shape for a particular application, okay? And this is just showing in some applications, although not typically with composites, if you were doing this double-sided, you come down from each side and you end up with an hourglass effect. That's all that's showing. Okay? But the key point here is notice the entry hole is always the same because it's defined by the mask. So that entry hole diameter is always the same. The exit hole is something that can be controlled because you can stop at any one point, and you can control that pretty much within about 25 microns or about a mil of spec. Okay? So a little complicated, but that's the process, if you will, from beginning to end. Now, one of the things that is critical in any application like this is that we can say one thing about the process, but it's great to have somebody else looking at what you're doing. So we've got some independent labs that have been looking at how this process works, what kind of stresses and what have you that you can put into it. And what these laboratories actually do, they're actually testing these composites long before they're perforated. They're coming out of the autoclave and they're testing them to make sure there aren't any stresses in them to begin with. Okay? But come to find out that the tools that they use for that are very useful to examine these materials after they've been perforated or machined. Okay? Now, some of the work that's been done externally, the two actual test labs, Mistress Group, uses a non-invasive ultrasonic scan, all right, in order to determine what kind of damage might be done to the substrate. Laser Technology Incorporated uses something they call shearography, also non-invasive, but it uses a laser to determine what kinds of stress might be in the material. And then independent from that, NASA has done some of their own work, independent from this process, to look at how they can reduce drag on engine liners. We're going to talk a little bit more about that because that's kind of an interesting study that's been done, but when we get to it. But let's first talk about the Mistress Group. What they did, they actually took a part that had been perforated and they did a non-invasive ultrasonic scan on it, and then they could do some micrographs and pictures to show what kind of stresses have occurred around each of the holes. And you can see, if you go around the peripheral of the hole, that it kind of goes out from the hole. And that's where we're talking about before. If you have these holes are much closer together, that can really be a problem and cause these composites to come apart. However, with the abrasive machining method, you can see that it's much more uniform, the stresses are much less, and the damage is much less. So that's a real plus. Okay. Then we go to the shearography test where they're using, again, the laser to do the non-invasive stress scans. And you can look at CNC drilling, water jet, and the abrasive method, and you can see the same effect. Different testing process, but showing the same effect. And notice how close these get together here when you're looking at CNC drilling and water jet. Actually here they're actually touching one another, so you've actually caused a joining between two holes of the stress and the damage internally that you couldn't see if you were looking at the composite. However, if you look at it with the abrasive method, because of the gentle approach that's taken as we scan gently through to create those holes, we don't see a lot of those stresses. Some, but very, very minor. Okay. And the way to illustrate that best is to actually look at, I'm going to put all three of these up at the same time because it's easier to show you. If you look at CNC drilling, and you look at a cross-section of the sidewall, you can see the kind of damage that occurs there, the tearing that occurs with drilling. And with water jet, you can actually see delamination occurring between the layers. Okay. However, the abrasive process shows all the sidewalls are clean. That's a big plus, and the aerospace people like that. Let me focus now on this NASA study that was done. Nothing to do with the process that we've talked about so far. However, the influence can be great. This is a study that was just completed actually in May of 2016, so it's a very recent study. And again, what they were looking at their Langley Research Center was how can we reduce the stress as air flows across the liners that are associated with jet engines. Okay. So what they did, this is a very quick overview of it, they took a typical honeycomb structure, laminated the composite to it as they normally would, and this already has all the round holes in it the way you normally would see it. And what they did was they measured as a reference the drag coefficient associated with the airflow across that substrate. Okay? And that became their reference point. That would be the typical coefficient of drag, if you will. Then they said, all right, suppose we reoriented or changed the pattern of those holes instead of using holes by themselves. So what they did then, somebody got this idea, well, let's just take those slots and go perpendicular to the airflow. And we'll line them up like we do, staggering them as we would have with the holes, and see what happens. What happened was they saw a 50% reduction in the coefficient of drag associated with what they call slots perpendicular to the airflow. And that was huge for them. How that translates into fuel economy has not been calculated yet, but you can imagine it can only have a positive impact on fuel economy. So in fact, we're hoping to get some more tests on that soon. But the fact of the matter is, this worked. So then the question is, it begs the question, all right, how do I put slots in composites? Can't drill them in, not easily. You might be able to CNC them, but they have to be very small. How do you do that? So what really became very exciting is that the abrasive process allows you to go from holes, just change the feature size on your photoresist, put slots in instead. Go through the same process that I just described earlier, and you get the end result that you're looking for. It doesn't cost you any more. It's very efficient to do it this way, and you hopefully get the same end result by doing that. The beauty of this whole test was, one of the things they also look at in these studies is acoustic capability of the liner. In other words, you don't want to increase the sound level by changing these features. So by going this route, they also showed that there was actually no loss in the acoustic benefits going from round holes to slots perpendicular to the airflow. Okay. So that was exciting, that there is in fact a process out there to make this work. Okay. And this is just showing again, the dry abrasive process can produce any perforation shape in the composites. Here's some examples of all kinds of shapes that you might think of. And again, that's just defined by that photoresist that we talked about earlier. That's what makes this happen. In fact, it wouldn't work without the photoresist. That's the key to the whole process. Here's just a couple of examples for sound deadening, blocker doors, holes being perforated, slot being cut in here, larger holes being put in here. That's all done at the same time with the photoresist applied to the substrate and then blasted using that process I showed before. It's all machined in a single step. This is another example of the honeycomb structure. We're looking at how can we apply the composite to the top of the honeycomb and blast it after it's been applied, which would be a big plus to the industry, because now what they do, they perforate it first and then apply it. Then they have to deal with the glue that's associated with it, oozing up through the holes and cleaning it out. If we do it the other way, apply the composite first, then blast it, we eliminate those problems. So that's a potential for us in the future. This one is an incredible application. I guess it's the best way I can describe it. We're in, and let's just say a vent in a helicopter, where you have to replace the screen that they typically take today, cut a hole in the composite. Then they have a metal screen that they have to rivet into place. Of course, they have to seal all that all the way around, and they have to put a grounding strap on it because it's metallic. And that's something that adds weight, a lot of process work going on, and what have you in order to make that. Well, if you look at the abrasive process that we just talked about, you now take that pattern, put it into the photoresist, and apply that mask to the composite, and go ahead and sandblast it, and now you have in fact created that same pattern into a composite material without putting any metal on it, no need for grounding straps, and you've reduced the weight, and you've reduced the time to produce it, and hopefully you've reduced the costs ultimately to produce these in larger quantities by using this process. Okay. And here's just a typical example of a liner that's been done with the process. The other part of this is that it doesn't have to be a flat piece. As you noticed before, you can do curved pieces. It doesn't matter because the robot is going to follow that curve depending on how the robot's been programmed. Now, the process does have some limitations. Let's talk about those just real quick. Resolution, you're limited to about 300 microns. For this industry, that's pretty good and not a problem. Feature size and tolerance, you can locate these features within 25 microns of each other. Again, for this industry, more than enough. Positioning of the features. You've got to remember these are huge panels, liners, and you can position all the features on that within plus or minus 50 microns. The maximum composite thickness is about a little under 1/4 inch. And why is that? Remember what I said before, as you're blasting down, you start to lose energy. So you can only go so far. A lot of this is related also to the hole size and what have you, because you know, the smaller the hole, the thinner that piece is going to have to be. So there is a thickness limitation, but again, for most of the composites used in the aerospace industry, not an issue. And again, the process works best on brittle materials. In fact, it only works on brittle materials if you really get down to it. Although you can do thin metal sheets if you wanted to do very thin film type metal sheets. It's not for solid metals, it's not for plastics, it's not, because they're ductile materials. They will act like the photoresist and they will repel the abrasive. So you can't use those in this process. This is just a comparison, and I don't plan to go through all these, but you can just see the traditional methods that we've talked about versus the precision abrasive machining. And the one thing we didn't talk about here, all these other ones we did talk about, was the ability to, if you have to make a design change. You know, you're in the middle of prototyping and you're trying to build something new and want to make a change. This process allows you to go in, quickly make a change on your computer to whatever feature you want, size, what have you, print out a new photoresist with the right features on it, and you're right back in business. So the turnaround is much quicker than it would be for conventional tooling systems. So with that, in a kind of a summary way, just to kind of take you back through what we've talked about today. We have a quick setup, very low tooling cost, essentially no tool wear. There are no tools to wear out in this process. No secondary deburring or cleanup is required. No delamination that occurs at all between composite layers, and that's a big item for the aerospace industry. It's a dry process. There's not any slurries or water used as you would do for, let's say, water jet technology. Uniform precision on all the holes and the cutouts, because they're all the same, okay? They're defined by the photoresist. High yields. All the holes are perforated. You're not going through drilling one at a time where you might have a broken drill bit and miss a hole. It doesn't happen with this process because they're all being done at the same time. Design changes are fast and flexible. We just mentioned that. High density features with no timing penalty. What does that mean? If I had a panel that had 100 holes in it, or I had another panel that had 1,000 holes in it, and I needed to perforate both of those panels, the time to do it is the same. Because of the way the process scans, it's defined by how many holes are in the photoresist. Okay? No stresses or heat buildup on the material, and it's a cost-effective process. Okay? So the unforeseen advantage that we talked about at the very end was this drag reduction and sound attenuation, which are things that are yet to come based on the results of the NASA study that was done. So we're very excited about the ability to work with NASA and, of course, aerospace companies to see how we can incorporate the results of that study into the actual process to make perforated composite materials. And so that's the discussion on precision abrasive machining. Again, non-traditional perforation for the aerospace composite materials. And at this point, I usually like to open it up for questions. But if you don't have any questions, you can contact our website, IKONICSAMS.com, and you can go on there and find out who to contact and probably answer some other questions that you might have. So thanks for coming. I appreciate it.